In this lesson, we are going to learn about number systems or bases. And this is something you already know about. You just haven't thought about it the way we're going to think about it today. So we'll talk about what a base is and how to convert between bases. We'll focus on binary and hexadecimal because those are the bases that we're really concerned about as programmers and computer scientists. These are the number systems or bases that come up all the time. And we'll also look at hex colors and RGB colors, and we'll understand what those two things represent and how to change from one to the other. We'll look at how to count in bases other than decimal, and we'll learn about bit shifting, which is something that we can do with binary numbers that also comes up in programming. And then finally, we'll look at how to add binary numbers. So first, let's start with what is a base. A base is just a set of digits that we use to express numeric values. We're really used to base 10 or decimal base. We have 10 digits in base 10. So in any base, we have as many digits as the base number. In base 10, we have 10 digits. In bases, the digits always start with 0. So in base 10 or decimal, we have the digits 0 through 9, and we're real comfortable with this. We're really used to it. With those 10 digits, we know that we can express any numeric value. And when we run out of digits, we don't run out of numbers, we just move to the next place. So when we count in base 10, we count from 0, we get to 9. We don't just have to stop there, we can keep going, we just have to move to the next place, and we get the number 10. And then we count 11, 12, 13, we get up to 19, and we still have more digits that we can increment in the tens place. So then we just go to 20, and we count from 20 all the way up to 99 until we get to the point that we've run out of digits in the tens place. And then we're not done, we're not out of numbers, we just move to the hundreds place and we get 100, and then we can continue counting in that way. And this is really natural for us. We're used to doing this, we just don't think about it. So let's look at another number system. This number system is very important to programmers. It's the binary system, or base 2. And like in decimal, in base 10, we have 10 digits. In binary, or base 2, we have 2 digits. Those 2 digits are 0 and 1. So in binary, what will happen when we run out of digits? Well, exactly the same thing that happens in base 10. So if we look at the table on the slide here, we have decimal in the left column. We're counting 1 to 5. And in the right column, we'll count in binary. So 1 is pretty straightforward. We can represent 1 the same way in decimal in binary. But what happens when we get to 2? We don't have a 2-digit in binary. Well, we've run out of digits, so we have to move to the next place. And we get 1, 0. So this represents 2 in binary. What about 3? Well, we still have another digit that we can increment in the ones place. So 3 is just 1, 1. That represents 3 in binary. What about 4? We run out of digits again, so we need to move to the next place, and we get 1, 0, 0. So what do you suppose 5 is? You may have guessed that 5 is just 1, 0, 1. So this may still look a bit odd and strange, and that's okay. It just takes some practice to get comfortable with how to deal with numbers in other bases. So let's try this approach. Let's think about place values. You may remember learning about place values in primary school. In any number, the place value is just the digit multiplied by its place in the number. So in base 10, we can think about the places, and those places are the ones place, and then the tens place, and the hundreds place, and the thousands place. And each one of these places, you'll notice, is an increasing power of 10. Why an increasing power of 10? Because we're talking about base 10. So the ones place is 10 to the 0, because any number raised to the 0 power is 1. The tens place, we have 10 to the first power. The hundreds place, 10 to the second power, which is just 10 times 10, which is 100, and the thousands place is 10 times 10 times 10, 10 to the third power, which is 1,000. So if we're asked what is the place value of 4 in this number 5,480, we get the place value by multiplying the digit 4 by the value of its place, which is 100, and we get 400. What about in binary? Well, we can do the same thing, and we can do the same thing in any base. So if we make a similar table, we would have a 1's place, and then a 2's place, a 4's place, an 8's place, 16's, and 32's. Why these values? Well, just like with base 10, for base 2 we have increasing powers of 2 in each place. So in the 1's place we have 2 to the 0 power, in the 2's place we have 2 to the first power, which is just 2. And then we have 2 to the second power, 2 times 2 is 4. Then we have 2 to the third power, 2 times 2 times 2 is 8. And we have 2 to the fourth power, so we multiply that 8 times 2 and we get 16. Then 2 to the fifth power, we multiply that 16 times 2 and we get 32. And this goes on. And the way that we would calculate the place value of a number, of a digit in a binary number, is the same way. So if we wanted to know the place value of this first 1 in the number 101100, we take the 1, we multiply it by its place value, which is its place, which is 32. We get 1 times 32 is 32. So that is the place value of this first 1, and that value is the decimal value of that place for this binary number. So let's, another way to think of this, determining the place value of a digit in a number, really what we're doing is we're converting from this number system binary to decimal. And we do that because then we can make sense of the number. Our brains aren't used to thinking in binary or hexadecimal or base 5 or base 7. We're used to thinking in base 10. That's what we can imagine. When we hear a number, if it's expressed in base 10, we can have some idea of what that number represents. So when we're calculating the value of a number in another base, what we're talking about is how do we represent that number in base 10. And so what we did in the last slide really was interpreting the place value of the first 1 in decimal. So we can convert any number in any base to base 10 using the same method that we just employed. That is, we write out the place value for each of the digits. So in this number, in this example here, we have the digits 1, 0, 1, 1, 1, 0, and this is a binary number representation. So if we represent each of the place values for those digits in the number, then we can write it out in expanded notation. You might remember that term from school, where we multiply each digit by its place value. So we get 1 times 32 plus 1 times 8 plus 1 times 4 plus 1 times 2. Now we have a 0 in the 16 in the 1's place, so we don't have to add those. We just get 0 there. So if we add the 32 plus 8 plus 4 plus 2, we get 46. And that is the value of this number 101110 in base 2 in decimal, 46 base 10. You might also notice that even binary numbers will always end in a 0, and odd binary numbers will always end in a 1. That's just a little something to notice, because of course that final number is the 1's place, and if we have a 1 there, we're going to have an odd number, and if we have a 0 there, we'll have an even number. So just something to notice. Now let's have a look at just maybe one more example to try to really make it clear what we're doing here. So if we look at an example like 10110, and we say that this is a binary number, and we want to know what is this number in base 10. Well, we can consider each of the places. So we have 1, 0, 1, 1, 0, and this is the 2 to the 0 place, the 2 to the 1 place, 2 squared place, 2 to the 3rd place, and 2 to the 4th place. And so this is, we have a 1 here, and here, and here. So these are the places we need to add up. So we have 1 times 2 to the 4th plus 1 times 2 squared plus 1 times 2 to the 1st. And that's the same as 1 times 16 plus 1 times 4 plus 1. And so that's 16 plus 4 plus 1, and that is 20. Oh, 1 times 2 to the 1 place. I got that wrong. You see that? That's 2, not 1. So 16 plus 4 plus 2, that gives us 22. And that's in base 10. Now, it can be useful. You see I just made that little slip up. 2 to the 1 power is 2. It can be really helpful to remember these first maybe 5 or 6 places in base 2. So if we start from the right, because that's the way we write numbers, let's just have a look at that. So we have 2 to the 0, 2 to the 1st, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th. Let's go up to 2 to the 6th. And we'll see here that we've got 2 to the 0, which is 1. Remember, any number raised to the 0 power is 1. We multiply that by 2, we get 2. We multiply that by 2, we get 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is 32. And 32 times 2 is 64. So these are the first places in a binary number. And if we can kind of remember those, it's not too hard to remember. Even remembering the first 4 is useful. Let's go one more and go 2 to the 7th. 64 times 2 is 128. So here we could say these are the, we have 4 digits down here at the bottom and 4 at the top. And each of these could be occupied by a 0 or 1. So if, for example, if we take the example 1, 0, 0, 1, then what we can see that we have here is 8 plus 1. Can you see that? Because we have zeros in the 4 and 2 place. We have a 1 in the 8th place and a 1 and a 1. So that's 8 plus 1, which is 9. So 1, 0, 0, 1 in binary is 9 in base 10. If we had 1, 1, 0, 0, what would we have? We have 8 plus 4, because we have a 1 in each of those places, and that's 12 in base 10. So if we can memorize these first 4 places, it can make it really quick for us to quickly translate those binary numbers into decimal. And if we have a bigger number, say for example we have 1, 0, 0, 1, 1, 0, then what do we have? Well, we have 32 plus 4 plus 2. So 32 plus 4 plus 2 equals 32 plus 6, which is 38 in base 10. So binary is easier than other number systems in some ways, because the digits are always either 1 or 0. So we're either adding that place into the result, or we're not adding that place because there's a 0 there. So this can really help us to quickly translate binary numbers into decimal numbers if we can kind of remember these first set of binary places. So let's go back and see what's next. Now, we also may want to convert from a decimal number to a binary number. So we've got a number represented in decimal, and we want to represent that as a binary number. So we have to do the opposite in this case. And there are 2 ways to do this, particularly when we're dealing with binary numbers. So this first way I'm calling method 1. And the way that we do this is we ask ourselves the question, what is the largest power of 2 that goes into this number that I'm converting, and I put a 1 in that place. So in this example, we're looking at the number 19 in base 10. And what is the largest power of 2 that goes in to 19? So let's have a look again at what we wrote up here. So if we look at what we wrote up here, what is the largest power of 2 that goes into the number 19? Well, 8 goes in, 16 goes in, 32 is too big. So the largest power of 2 that goes into 19 is 2 to the 4th, or 16. So if I put a 1 in that place, then I know I'm adding a 16. Now, then I ask myself the question, what's left? If I take 16 out of 19, what's left? So 19 take away 16 gives me 3 left. So what's the largest power of 2 that goes into 3? Well, that would be 2. So I have a 1 in the 2's place. So now I've added 16 plus 2. That gets me to 18. So I still need 1 more. So I put a 1 in the 1's place, and then I get my 19. So I fill in zeros everywhere else. And so now I end up with 10011 in binary represents 19 in base 10. So this is what I call the first method, and it works well with binary because we only have 1s and 0s as digits. This way gets to be a bit trickier if we're dealing with a base bigger than 2. So I only like to use this method for base 2. Let's just look at another example quickly. What if I had the number, I'm going to do it over on this side. What if I had the number 143 in base 10? Well, what is the largest power of 2 that goes into 143? Well, I can fit 128 in there, so I put a 1 in the 2 to the 7th place and the 128 place. And if I take 128 from 143, what's left is 15. So I have 15 left. How do I represent that 15 in binary? Well, 16 is too big to fit, so I can't fit a 64 or a 32 or a 16, but I can fit an 8. And if I take 8 from 15, that leaves 7 left. I can fit a 4 in there. And if I take 4 from 7, that leaves 3 left. So there's my 2 and my 1. So the number 143 in base 10 can be represented by 128 plus 8 plus 4 plus 2 plus 1. So 1 0 0 0 1 1 1 1 gives me 143 in base 10. Let's look at another way of converting a decimal to binary that I'll call method 2, and it works really well for any base conversion from decimal to any base. So let's look at method 2. Decimal to binary, and this works for any conversion from decimal to any other base. And this is the divide method. So in the divide method, what we do is we start with our number. So let's look at the example of 19 in base 10. And we're going to divide this number by the base until we can't do it anymore. So let's see what I mean. So we start with 19. We divide that by 2 because that's the base we're trying to convert to. And 19 divided by 2 is 9. And then we keep track of the remainder. So how many are left over? 2 times 9 is 18. 18 from 19 is 1 left over. So in base 2, our remainder is always either going to be 1 or 0, right? It either is an even number and divides evenly, or it's an odd number and it doesn't divide evenly. We have 1 left over. So then after each step, we ask ourselves the question, this quotient, can we divide it by 2 again? Is it bigger than or equal to 2? And it is. So then we take the 9 and we divide by 2 again. And in this case, we get a 4. 4 times 2 is 8. That gives us a remainder of 1. Then we take the 4, because 4 can also be divided by 2. It's still bigger or equal than 2, and we get a 2, and this time we get a remainder of 0. Now 2 can still be divided by 2, so we have to keep dividing until our quotient is less than the base that we're trying to convert to. So we say 2 divided by 2, that gives us a 1 with a remainder of 0. And now we're down to 1. This number can no longer be divided by 2, it's less than 2, so we're done. And then our answer starts with the last quotient. So we have a 1, and then we go backwards through the remainder. So the next number is 0, 0, 1, 1. So this is the number in binary. And 10011, if we look up at what we did the first time, here's our 19, 10011. We got exactly the same thing. 10011. So this is another method of converting from decimal to another base. We divide until the final quotient is less than the base, and we keep track of the remainders. The answer is formed by, it starts with the last quotient, and then we add on the remainders in reverse order that we got them, and that gives us our number in the other base. So again, this might still seem a bit strange and unusual, but it's just something that you begin to learn with practice. So you just have to keep practicing, and it starts to become comfortable. So I encourage you to do lots of practice. So let's move on now, and we're going to talk about hexadecimal. Hexadecimal is base 16, and I'm sure you've heard of it before. So base 16 is interesting because it has 16 digits, and we're really only used to seeing 10 digits. So in hexadecimal, we start with 0 through 9, just like we do in base 10, but then we have to start using letters. So in hexadecimal, the decimal number 10 is represented by A, 11 is B, 12 is C, 13 is D, and 14 is E, 15 is F. Why do we just go up to 15? Because in hexadecimal we have 16 digits total, starting with 0. So our final digit represents the number 15, and so we go from 0 through F in hexadecimal. So I would strongly suggest that you get really comfortable, memorize the decimal numeric and decimal to letter representations in hexadecimal for the numbers that are the digits past 9. So just really get it in your mind, or write it down every time until you do get used to it, that A is 10, B is 11, C is 12, D is 13, E is 14, and F is 15. So to convert from hexadecimal to decimal, it's just like converting from any base to decimal. So we have a number, and a lot of times hexadecimal numbers are represented with this notation. They start with the number 0 and then the letter X. So 0x just is a notation that indicates this is a hexadecimal number. So here the number is 2CB. And that's the hex number, and we want to convert it to base 10. So just like we did before, we write out the number 2CB, we put it in a table with the place values for hexadecimal or base 16. So in the first place, the rightmost place, we have the ones place, 16 to the 0 power. Then we have 16 to the first power, that's the 16's place. And then the 16 squared place comes next, which is 16 times 16, 256. So to convert this number 2CB to decimal, we have to multiply 2 times its place value, its place, 256. Add to that C times its place, which is 16. Now, we can't multiply C times a number, so we have to remember that C is 12. So remember that C is 12, and we multiply 12 times 16. And then B, we have to remember that B is 11. And then we multiply 11 times 1. So we have 512 plus 192 plus 11, and that gives us 715. And if we had a larger number, then we would just have to multiply it by increasing places, and we would get a very large number very quickly. You can probably imagine. So let's look at hexadecimal colors. Hexadecimal colors you would have be quite familiar with by now as a web developer, and they're represented starting with a hash symbol, and they have 6 digits typically. There are other forms. We might see 3 digits when digits are repeated and so forth, but let's just consider the typical 6-digit hexadecimal color value. So in this representation, you may or may not realize that the first 2 digits represent the red component of the color, and the second 2 digits represent the green component, and the third 2 digits represent the blue component. So in this example where we have 0122FF, 01 represents the red component, 22 is the green, and FF is the blue. Now these are hexadecimal values. So if we wanted to know what color this represents in RGB format, we would convert each of these hexadecimal values into decimal, because RGB format is a decimal color format. You may not have realized that. So we start with red. We have 01. Well, 01 in hex is just 1 in base 10. So we just have 1 there times 16 to the 0 power, or 1, so we just have 1 in base 10. Now if we look at the next, the green component, we have 2, 2. So 2, 2 in hex is 2 times 16 plus 2, and we get 34. So that's 34 is the decimal representation of 2, 2 in hex. And then finally, FF for the blue component. Now FF, if we look back, F is 15. So to calculate FF, we have to multiply 15 times its place, which is the 16's place, and add to that the 15 that's in the 1's place, and that gives us 255. So 255 base 10. So the RGB color that represents 0122FF in hex is RGB 134 255. Now, if I asked you the question, what is the largest value for any one color? So for red or green or blue, represented in hexadecimal, what is the largest value? Well, we would determine that by determining what are the largest digits we can put in those 2 places, and that would be FF. So FF is the largest value that we can represent for a color component, for red, green, or blue. In decimal, that is 255. 255 is the largest numeric representation in decimal that we can have for a particular color component, red, green, or blue. Now there's an interesting relationship between hex and binary numbers, and that's because hex 16 is a multiple of 2, or it's a power of 2. 16 is a power of 2. It's 2 to the 4th power. What that means is that one hex digit, which can represent up to 15, is equivalent to 4 binary digits. So if we look here at this table, in the top row, we have hex numbers from 0 to F. Those are all the hex digits, all the single digits that we can represent in hex. If we look at the binary equivalents, we can see that the binary 0 is just 4 zeros, and then we have 1, 2, 3, 4, all the way up to the largest binary value we can represent in 4 digits, which is 15. 8 plus 4 plus 2 plus 1 is 15. What this means is that when we are converting between hex and binary, we can do it one digit at a time, and this is really convenient. So let's look at an example. If we have a hex number 5A3, and remember that this 0x notation is just notation to indicate that this is a hex number. So 5A3, what we can do is convert each one of these digits into binary to come up with the binary representation of this hexadecimal number. Now we can only do this between hex and binary. We can't do this between decimal and binary, or hex and another base, only if the two bases are a power or root of each other. So in this example, we get the binary representation of 5, which we can see from this table is 0, 1, 0, 1. 4 plus 1 is 5, so 0, 1, 0, 1. A, remember that A is 10 in hexadecimal. Here's A, and we get 1, 0, 1, 0. That's 8 plus 2 is 10, 1, 0, 1, 0. And then finally 3, and 3 from the table is 0, 0, 1, 1. That's 2 plus 1 is 3, 0, 0, 1, 1. So we can easily convert from any hex number to binary and back. Let's have a look at a couple more examples like that. So hex and binary have a special relationship. If, for example, we have the hex number A37, then we can take each one of these digits in hex and write down the binary representation. So first of all, we have to remember that A is 10, and 10 in binary is 8 plus 2. You see what I did there? So this is me remembering that these first four digits, 8, 4, 2, and 1, are the place values for binary. So I can just think of which numbers do I add up to get this value in this hex digit, and I put ones in those places. So for 10, I have 8 plus 2, and I get A. What about for 3? For 3, I need 2 plus 1. So there's the 2 place and the 1 place. And what about for 7? Well, 7, I have a 0 in the 8's place, and then I have 4 plus 2 plus 1. And that gives me 7. So A37 in hex is 1, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 1 in binary. Likewise, I can go from binary to hex. So if, for example, I have the number 1, 1, 0, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 0, 1. So that's a nice big binary number, and I want to convert this to hex. Then I just take each digit. So 1100 is 8 plus 4, which is 12. And then I have to remember, I might make myself a little cheat sheet over here. A is 10, B is 11, C is 12, D is 13, E is 14, F is 15. So 12 is C. So this one is C. 1010, we have an 8 and a 2. That's 10, and 10 is A. 1111, can you remember what 1111 is in binary? That's the biggest 4-digit number that we can represent in binary. That's 15, and 15 in hex is F. And then 0001, which is just 1, which is also 1 in hex. So this number in binary is 0x, just for the notation, CAF1, CAF1 in hex. So just to remember, you can only do this type of single digit conversion between hex and binary. You could also do it between base 8 and binary for the same reason that 8 is a multiple of 2, but you can't do it between hexadecimal or decimal and binary. That's important to remember. Now, what if we have to convert between two non-base 10 numbers? What do we do then? To do this, we're going to have to go through a base 10 conversion. What do I mean by that? We look at the example 58 or 5/8 in base 9, and we want to convert that to base 5. We can't go directly between base 9 and base 5. First, we have to convert the base 9 number to decimal, and then we can convert the decimal number to base 5. So if we take 5/8 and we convert that to decimal, we do that, remember, by multiplying each number, each digit, by its place. So in base 9, we multiply 5 times 9, and then we add to that 8 times 1. We get 45 plus 8 is 53. This is in decimal, so 5/8 in base 9 is equal to 53 in base 10. Then we convert 53 from base 10 to base 5, and we'll use the division method for that. So we take 53, we divide it by 5, we get 10, and we have a remainder of 3. Then we divide 10 by the remaining 10 by 5, we get 2 with a remainder of 0. And we can't go any further because 2 is less than 5. So we write down the 2, then the 0 remainder, and then the 3 remainder, and we get 203 in base 5. Let's look at another example or two like that. So if we're converting non-base 10 numbers, let's look at the number, we'll look at the number 2, 3, and base 4. So the number 2, 3, and base 4, and let's say we want to go to base 7. So the first thing we have to do is convert 2, 3, and base 4 to base 10. So step 1, convert 2, 3, and base 4 to base 10. And we do that by saying 2, 3 is the same as 2 times 4 to the first power plus 3 times 4 to the 0 power, or 2 times 4 plus 3 times 1, which is 8 plus 3, which is 11. So that's the value in base 10. So 2, 3 in base 4 is equivalent to 11 in base 10. Now we're going to convert 11 in base 10 to base 7. And to do that, we need to divide 11 by 7. So remember, base 10 to another base, we use the divide method. So we divide 11 by the base 7. 11 divided by 7 is 1, and we have a remainder of 4. And since 1 is less than 7, we're done. So we write down the last quotient and the remainder, and that is our number in base 7. So 2, 3 in base 4 equals 1, 4 in base 7. Again, this might still seem a bit strange, and what you need to do is practice. So there's lots of practice available. We'll have some worksheets, and you just need to do those worksheets and do the practice, and it will become more familiar. Let's talk about counting. So when we look at counting, we just have to think about what we do when we run out of digits in the base. So when we're counting in hexadecimal, for example, we count from 0 through 9, and then we have to use A, B, C, D, E, F. as we learned before, and F takes us up to 15, which is the last digit in hexadecimal. So what comes next? When we run out of digits, then we move to the next place. So what comes next is 1, 0, then 1, 1, 1, 2, 1, 3, all the way up to 1A and 1B and 1C and 1D, 1E, 1F, then we go to 2, 0, and so on. What about base 13 in the second example? In base 13, we use the first 9 digits, and what comes next? Well, we're in base 13, so we need to have digits representing up to the number 12. So what do you think would come next? Well, we would get an A, a B, and a C, and that would take us up to 12. What would come after that? We've run out of digits, so we go to the next place and we get 1, 0, 1, 1, 1, 2, 1, 3, all the way up to 1A, 1B, 1C, and then we'd have to go to 2, 0. What about bases that are less than 10? So if we look at base 4 in this example, we start with 0, 1, 2, 3, and then we've run out of digits because base 4 only has 4 digits, 0 through 3. So what comes next? We move to the next place and we get 1, 0, 1, 1, 1, 2, 1, 3, then 2, 0, 2, 1, 2, 2, 2, 3, 3, 0, 3, 1, 3, 2, 3, 3, and so on. So that's the way that we count in bases, and also just takes a little bit of practice and getting familiar with that because it's a bit strange. We're not used to thinking about numbers in other bases and counting in other bases. Let's talk about bit shifting. Bit shifting is something that we do with binary numbers. Sometimes we call binary numbers bits. When we have 4 binary numbers, when we have 8 binary numbers, we call that a byte. So a byte is 8 bits. So bit shifting refers to a manipulation that we can do with binary numbers. So there are 2 shift operators. The first one is to right arrows or greater than arrows. And when we have a binary number that's shifted right some number of places, the number to the right of the arrows tells us how many places we're shifting. So when we shift to the right, what we do is we're dropping bits off of the right side of the number. So when we bit shift the number 1000 2 places to the right, it means that we move all the bits 2 places to the right and the last 2 bits fall off. Another way of thinking of that is we remove the last 2 bits, we end up with 10, which is the number 2 in base 10. When we shift to the left, we are adding zeros to the right side of the number. We're adding bits to the right side. So if we have the number 100 in base 2 and we shift it to the left by 1, then we add 10 to the end. Another way to think of it is we're moving all the bits to the left 1 place. And if we bit shift 100 1 place to the left, and then we end up with 8. So let's look at some examples of this. Just a couple more examples so that it gets to be a little bit more clear. Now, one thing you may have noticed when we're bit shifting is that we have to do it with bits. So let's start with an example where we start with a binary number like the one we just looked at. And just make sure that we're comfortable with it. So if we have, for example, the number 11001 and we shift that to the right 3 places. Basically what it means is that you can think of this this is an edge to the right of the number here. We have an edge, and if we shift to the right, then we move beyond this barrier and the numbers that get shifted past the barrier disappear. So we're shifting all of these bits, 11001, to the right 3 places. So we shift off 1100. The 1 gets shifted off first. That's 1 place. then 1, 1, 0, 2 places shifted off, and then 1, 1, 3 places shifted off. So what we're doing is we're shifting the last 3 bits beyond the edge of the number is one way to think of it. We're moving the whole thing to the right, and there's an edge here that once we go past, we lose those numbers. So these numbers disappear off the number, and they're no longer stored in memory. This is what's happening in the computer, and what's left is just this 1, 1. So this gives us 1, 1 in base 2. Remember that this is a binary number. And what is 1, 1 in base 2? Well, it's 2 plus 1 is 3 in base 10. So this is shifting right. Shifting right, our number, the number we start with, gets smaller. So here the number we started with was 11001. That is 16 plus 8 plus 1, which is 25. So we started with 25 base 10, and we ended up with 3 base 10 when we did the shifting to the right by 3. So shifting to the right, we always end up with a smaller number because we push numbers off of that edge of the register. Shifting to the left makes the number bigger. Shifting left. So if, for example, we have 1, 1, 0, and we shift it to the left 3 places. Then what we're doing, so we've got the edge here, but what we're doing when we shift to the left is we're moving all 3 of these digits left 3 places. So we move it left 1 place, and we fill this in with a 0. Then we move it left another place, and we add another 0. And then we move it left another place. So this is 1. We move it left another place, and we fill in with another 0. So we're shifting the bits left, and we're filling in the right with zeros. So we end up with a bigger number. And so we started with 110, which is 4 plus 2, so that's 6 in base 10. And we end up with 32 plus 16, which is 48 in base 10. So we go from 6 in base 10 to 48 in base 10. Our number gets bigger when we shift to the left. So the number gets bigger when we shift to the left, and the number gets smaller when we shift to the right. So I wanted to sort of demonstrate this shifting that we're doing, and that we're sort of in this register that that when we shift to the right, the numbers fall out. But you can also just think of it, when we're shifting right, we take off the digits that we're shifting by from the right-hand side, and we add zeros to the right-hand side when we're shifting left. There are 2 different ways to think about that. Now, what if we're given a problem like this? We're given a problem like 32. Whenever we see a number like 32, if no base is given, we can assume it's base 10, and we're asked to shift it to the right, 3. Well, we can't bit shift a decimal number. We can only bit shift a binary number because we're shifting bits, and bits are binary. So the first thing we have to do is convert to binary. So if we convert 32 to binary, what do we get? Well, we think about our places. So we have the 1's place, 2, 4, 8, 16, 32. We don't need to go any further. So we put a 1 in the 32 place, zeros everywhere else, and that is 32 in binary. So if we shift that 3 places to the right, we basically move our edge from here to here. We take off these last 3 numbers, and we end up with 100, base 2, and that is 4 plus 0, so that's 4 in base 10. So 32 base 10 shifted to the right 3 gives us 4 base 10. We had to convert to binary first, then we shift. And we end up with 4. Okay. So hopefully that's a little bit clear. Again, it just takes some practice. There'll be some practice for you to do. And it becomes more comfortable with practice. Finally, we're going to look at adding binary numbers. So the first thing we'll do is that we'll remember how we add decimal numbers. And then we'll just apply the same process to binary numbers. So let's have a look at some examples of that. Adding. And we're only going to worry about adding binary numbers. We're not going to worry about decimals or anything else or other bases. We're only going to look at adding binary numbers to get a sense of how we do it. So first let's look at an example with decimal. With decimal numbers, we have, for example, if we had 2,671 plus 2,539. If we added these two numbers together, then we would start from the right-hand side from the ones place, and we add 1 plus 9, we get 10, and when we get a number that's bigger than the largest digit in that base, then we carry the 1, right? We carry the 1 to the next place, and then we add it to the next column of digits. So then we have 7 plus 3 is 10, plus 1 is 11. So we put the 1 from the ones place in 11, and then we carry the 1 that's in the tens place to the next place. So then we get 6 plus 5 is 11, plus 1 is 12. We put down the 2 that's in the ones place, and we carry the 1 that's in the tens place to the next place, and we get 2 plus 2 is 4, plus 1 is 5, and we get 5,210. And we probably all know how to do that. Well, in binary, it's just the same. So let's consider that we have these two numbers. Say we have 1, 0, 1, 1, 0, 0, 1, 1, 1. And we want to add to that 1, 0, 1, 1. Well, just like decimal, we start from the right-hand side, from the ones place, and we add 1 plus 1. That gives us 2, but we can't write a 2 here because this is binary. No, how do we represent 2 in binary? Well, there's a 0 in the ones place and a 1 in the twos place, right? Because 2 is 1, 0 in binary. So we put the 0 from the ones place and the 1 from the twos place and the next place over, the next column. So then we have 1 plus 1 plus 1, and that's 3. What is 3 in binary? 3 in binary is 1, 1. So we put the 1 that's in the ones place and we carry the 1 that's in the twos place. Then we add 1 plus 1 is 2. So we put the 0 that's in the ones place and carry the 1 that's in the twos place. 1 plus 1 is 2. We put the 0 that's in the ones place and carry the 1 that's in the twos place. 1 plus 0 is just 1, and then 1 plus 0 is 1. So we end up with 1, 1, 0, 0, 1, 1. Now, if we wanted to convert that to decimal, what would it be? Well, what places do we have? We have the ones place, 2, 4, 8, 16, 32. So it's 32 plus 16 plus 2, because that's where we have ones, here, here, and here. And so that is 48 plus 2 is 50 in base 10. Now, we weren't, we didn't have to do that conversion. I just wanted to sneak in the little practice of binary to decimal. So that's it. That's all that we're going to cover in this lesson. All there's left to do now is to practice. And before you know it, you'll be a whiz at converting between bases.